Organic chemistry. It's a two-word title that elicits so much angst and pain from so many different people. Even mentioning organic chemistry to many college graduates and people who've gone through it is a painful experience. But the organic chemistry that we learn in AP chemistry is really not that difficult if you try to understand exactly how it works. As the great Andrew Dado once said, it's a puzzle. And yes, he's right. It is a puzzle. And do you know why it's a puzzle? It's a puzzle because there's nothing to it. There's very little calculation to do. There's very little memorization to do, although there is a little bit. What it really is an intelligent person, or you don't have to be intelligent, but anybody looking at a string of molecules and figuring out where to start and how to calculate that string of molecules. Now, what I said might not make a lot of sense, but it will make a lot more sense once you delve deeper into it. All you really need to do is use your common sense. That will help you so much more than reading a textbook for a topic like the one we're about to discuss. So let's get into it, alright? Now, I just want to go back on something I said earlier, that there's no memorization involved. That's not explicitly true. There's a decent amount of memorization, especially at the beginning. But what makes this memorization so easy is that it's all sensible. See, in a lot of different topics, a lot of different subjects, the memorization you get is sort of rote memorization. You know, when you're memorizing equations for math class, or for chem class, or for physics class, or for biology, or you're memorizing, I don't know, conjugations of verbs in Spanish or French, or other things like historical dates. You really need to memorize it. There's not that much common sense that goes into knowing what year this and this happened. I mean, you can infer it sometimes, but a lot of times you just have to memorize. But for organic chem, the memorization, especially at the beginning, is very simple. I'll go through it right now. Alright, first thing you need to know, the names of every molecule are based on the number of carbons in the longest chain on that structure. Meaning, if the longest chain on a molecule has, say, 4 carbons, it will be called butane. And if the longest chain has 5 carbons, it will be called pentane. We'll get into what longest chain means in a little bit, but first I just want to give you the draft, the layout of the names of each of these molecules. 1 carbon is methane. 2 carbons is ethane. 3 carbons is propane. 4 carbons, as you already know, is butane. 5 is pentane. 6 is hexane. 6 right there. 7, heptane. And for those of you who know your Greek and Latin stems, you'll know that 8 is octane. That 9 is nonane. And that 10, the big 10, is decane. Now, for the first 4, there is a little bit of memorization that goes on, I'm not gonna lie. You need to memorize that 1 carbon is methane, 2 carbons is ethane, the 3 carbons is propane, and the 4 carbons is butane. So, do you have that? That's all the memorization you really need to know. Because, for the next few, just look at what comes before. Now, all of you should know pent is 5, hex is 6, hept is 7. That's basic stems and roots. So knowing that, you can infer 5 is pentane, 6 is hexane, 7 is heptane, 8 is octane, 9 is nonane, 10 is decane. A little bit of common sense gets you a long way in this unit. But right now, I want to talk to you about what longest carbon chain actually means. Alright, before we get into what longest chain actually means, we need to understand that what we were just talking about, the nonanes, the decanes, the octanes, those as a group are called alkanes. Now, alkanes are basically strings of carbons surrounded by hydrogens, meaning that at any given point, a carbon is surrounded by a number of hydrogens depending on how many bonds it has. If you think about it, it's basically a line connected by a bunch of dots. Or if you want to think about it differently, it's a zigzag. And every point, every crest, peak, every trough, every denier is a carbon. People often write it as a zigzag as a lightning bolt, so to speak, sideways lightning bolt, because it's a lot easier than just drawing carbons and hydrogens next to each other. So basically, if you have a zigzag, it starts here, goes up, goes down, you don't see it, and ends here, so it's like this, 1, 2, 3, 4. That, if you can guess, is a butane molecule. And the reason for this is that you have one carbon here and it goes up, that's another carbon. It goes down, that's a third carbon, and then it ends with the fourth carbon. So knowing this, it's a lot easier to figure out what longest carbon chain actually means. Often, molecules, especially alkanes, have a lot of what's known as subgroups, or branchings, so to speak. In the same way that a branch splits off into a lot of different mini branches if you look on a tree, so do alkanes often branch off into a lot of different carbon chains, mini carbon chains. And I'll show you a little bit of a drawing to more easily express my point. Now what you see here is a typical branching of an alkane. First carbon is here, second is up here, third is down here, the fourth is right at this junction here. But you don't know, or at least you don't think you know, which direction to go. Now the easy way to figure this out is you already have 4. 1, 2, 3, 4. Which one of these routes, or branches if you so call it, contains the most carbons? Does this one? It ends with one more. So if you took this branch, took this route, or whatever you want to call it, you'd end up with 5 carbons in the chain. So 1, 2, 3, 4, 5. However, if you went this way, 1, 2, 3, 4, 5, 6, you'd end up with 6 carbons. Now the longest chain on that molecule is 6 carbons. Therefore, in determining what type of alkene it is, you use the 6 carbons rather than the 5. So, as a base molecule, that alkane there would be, you're right, it's a hexane. If you said anything else, you're not very attentive. I think it's time to move on. I think you guys have got it down, at least this part. So I'm sure some wise guy in the crowd's up there with his arm up, yelling, "Oh, but there's still a carbon that you didn't account for!" Yeah, you're right. There's a carbon on that carbon chain that I just showed you that we didn't account for. Now, we said it was a hexane, but there's yet another carbon. Alright? Let's look at the diagram once again. Alright, so if you remember, we made a hexane molecule out of this. 1, 2, 3, 4, 5, and 6. But there's still this one right here that's gone unaccounted for. How would you solve this problem? The first thing to do is to calculate the length of that group that went unaccounted for when you calculated the longest carbon chain. In the diagram that we showed you, there's only one more carbon that didn't go unaccounted for. You see this junction carbon here, there's this one. Now, does anybody know what the name of a 1-carbon alkane is? Methane! That's right, boys and girls. It's methane. That subgroup that went unaccounted for is a methane subgroup. But the catch is we don't call it methane. We drop the ane and add on a Y and an L. So in this case, that would be a methyl subgroup, M-E-T-H-Y-L. If it had, say, 5 carbons, which is not very common, but if it did, it would be a pentane subgroup, but you drop the A and E, add the Y and the L, and you'd call it pentyl. If it was butane, it would be butyl. Propane is propyl, and so on. So basically, you've got this pretty easy system of determining the name of both the longest carbon chain and the substituent groups. Once you have all of that down, the last thing you need to do is figure out what position on the longest carbon chain that substituent group or those substituent groups are. And when I say position, I mean at which carbon on the longest carbon chain does the substituent group branch off of. In the picture here, you see the first, the second, the third, and the fourth. The junction is at the fourth carbon. That's where it branches off. But here's a little trick. The answer is not actually fourth carbon. Does anybody know why? The answer is you start counting from the side closest to the end of either side of the carbon chain. Because if you think about it, you could technically start from either side, and it could be at the fourth carbon or it could be at the second carbon. Right. Actually, the third carbon, but it doesn't really matter. Instead of starting here, 1, 2, 3, fourth carbon, start up here. 1, 2, 3. The reason that you start up there is because it takes fewer carbons to get to the juncture. If it takes an equal amount from either side, you can do it from either side because there's no difference. That is, unless you start getting into multiple substituent groups, but we'll talk about that a little bit later. So how would you name this element? Well, you know first of all that it's a hexane. So that's one part of it. You know the substituent group is a methyl group, so that's the second part. And now you know that it's on the third carbon of the carbon chain, and that's the last part that you need to know. The molecule right here, you'd call 3-methylhexane. 3-methylhexane. And that's the name. It's pretty simple if you think about it. It's just got a few different parts that you need to know. But it gets a little bit harder. This was a relatively simple molecule to deal with. Where it gets tough is where you have multiple substituent groups of varying lengths and multiple ones of the same length. So let's look at an example. So now take a look at this bad boy right here, alright? First, before we do anything with multiple substituent groups like I was talking about, we need to figure out how long the longest carbon chain is, just as before. So we can start on either side. Let's start here. So now, an inquiring mind might ask, which of these do you start with? Because this one has 2 carbons, 1, 2, before it hits the junction. This one also has 2 carbons, 1, 2. Well, the answer is you can start with either, because it really doesn't matter. Because at both of them, you're going to have a substituent group branching off at what is the third carbon. So you can do either, it doesn't matter. So let's start counting. 1, 2, 3 carbon, 4, 5, now don't go this way, 6, 7, 8. So it's an octane molecule. But there's still a few things you need to add on to it. It's not just an octane molecule. Let's look again. You see first the fact that at the 3 you have a substituent group branching off. Now, what's got 2 carbons? Which means it's an ethyl group. Let's look again. So at the third carbon, you have an ethyl. 4, 5, methyl. 6, methyl. And then 7, 8. The thing is, you don't start from here. You start from over there. Now, again, you might ask, well, it's the same for here as it is for there. It's at the third carbon here, it's at the third carbon as well. The first substituent group. Well, the answer to that question would be, there's another substituent group right here, coming off at the fourth carbon, and here, it's at the fifth. So you're going to start from over here because the second closest substituent group, which is this methyl right here, is at the fourth carbon. So we know the locations of all the groups. Now it's just a matter of putting it all together. So you start counting at 1, 2, 3. You have a methyl, so 3-methyl. Whoa, 4-methyl. 5, 6 ethyl octane. But the thing here is that you can't just go 1, 2, 3 methyl, 4 methyl. It's not 3 methyl, 4 methyl. It's 3, 4 dimethyl, 5, 6 ethyl octane. But there's a couple conventions that you need to follow first. One of them is that ethyl comes before methyl, at least you say that, because E in ethyl is earlier in the alphabet than M in methyl. It's kind of stupid, but that's how it works. So it'd actually be 6 ethyl, 6 ethyl, 3, 4 dimethyl octane. So yeah, something as complicated as this can be turned into something as relatively simple as a few numbers and a few words. Now again, it may look really complicated, but once you understand it, it's really quite simple. More to organic chemistry than just this. Multiple bonds. So far we've been dealing with carbons that have only had single bonds between them, but there is often, in organic chemistry, multiple bonding, double bonding, triple bonding. I guess in some cases even more than that, but we don't get into that. So let's talk about bonds. Now what you see here is a double bond. I've seen these single bonds before, just about everything we've done, but you haven't seen this yet. This is the notation, or rather how you draw a double bond. Just a little line next to the normal bond. This right here is a triple bond. Now obviously the lines would be straight, but I can't draw straight, so there's that. This is how you draw a triple bond. Now, bonds themselves don't have a name, but what we've been working with before were called alkanes, if you remember. They were all single bonds. These that we're working with right now are not called alkanes, they're called alkenes if they're double bonds, or alkynes if they're triple bonds. Alkene is spelled E-N-E instead of A-N-E, and alkyne is spelled Y-N-E instead of A-N-E. So the bonds right here, or rather the molecules right here, would be called, say, instead of heptane, you'd call it heptene or heptyne, depending on whether or not a double or triple bond existed. Now, there's not going to be any situations in which you have both a double or a triple bond, and there's not going to be any situations in which there's going to be a quadruple bond, because I don't think those even exist. But you still have to know how to write and how to say and how to name the molecules that have double or triple bonds, and it's pretty simple. You basically use the same tactics that you used before, but with a little bit of alteration. The first thing to know is that you always have to take a path with all the double bonds in the molecule. Before you just took the longest path, and here it still applies to an extent, but if there's a shorter molecule that has a double bond in it, then say if you have an octane and it has an 8, and say you have another branching off, let's say the third in the octane, and you have a double bond going to a carbon, and that would make for a hexane. You go with the hexane because it has the double bond. That's rule number 1. Rule number 2 is that you always start from the side in which the double or triple bond is closest. Before you'd start with the side that had the closest subgroup, methane branch or an ethane branch or a methyl or ethyl branch, I guess you could say. But here you start on the side that has the closest double or triple bond. And lastly, instead of counting the carbon at which, say, a double bond begins or ends, you count the string or the bond that it's on. And let me show you what I mean. So let's take a look at this molecule right here. It's a butane because it's got 4 carbons. But it's got a triple bond right here, so you'd call it a butene, a butyne, with a Y. But think about this, alright? Somebody might ask, well, what do you call it? Do you call it 1-butyne because that's where the triple bond starts, or do you call it 2-butyne because that's where it ends? Well, the answer is you call it 1-butyne. Not because it starts here, but because this is the bond along which it goes. There's 3 bonds, so to speak, in this molecule. There's this one right here, there's this one right here, and then there's this one right here. So instead of counting the carbons, you count the bonds. Of course, if there was a methyl subgroup coming off of here, you'd go 1, 2, 3. So it'd be 3, say, methyl 1 butyne. 3 methyl 1 butyne. So you can still do it for the actual subgroups, but not for these little bonds. So let's do an example. How about this bad boy right here? So obviously the first thing to do would be to count the longest chain. 1, 2, 3, 4, 5, 6, 7, 8. It's an octane. One thing I could have done here that I didn't was draw a longest chain and then a shorter chain with the double chain or with the double bond to better show the process of selecting which chain to use. But this is just, the longest chain also has a double bond in it, so you just have to live with it. Alright, so you got an octane. But since there's already a double bond, you're going to call it an octene. That's the first thing. The second thing is deciding where to start. Do you start here, or do you start there? Well, here it's true you have a methane branching off of the 3rd carbon. Here at the 3rd carbon there's nothing. But there's the butene right here. So you start over on this side rather than this side because the double bond is closer than it is over there. So let's do this. It's 1, 2, 3. That's where the double bond is. And then you go back and count the carbons. 1, 2, 3, 4, 5, 6. So it's 5, 6 dimethyl 3 butene, or not butene, octene. So 5, 6 dimethyl 3 octene. Sorry about that. So that's basically what you have. It's pretty simple. It's just an extension on things that we already know. Next is going to be cyclic molecules. Ooh, that's cool. Alright, young Padawan. Cyclic molecules. Well, cyclic molecules are basically same as what we've seen before. The arrangements of carbons and hydrogens that orient themselves in such a way as to form a shape, or not a line, but something that has no beginning and no end. So it's not a circle because obviously circle has infinite sides, but say a triangle or a square or a pentagon. The same rules apply to cyclic molecules as do to alkanes, alkenes, alkynes. There's even often double bonds and triple bonds in cyclic molecules, which you'll have to account for. Anyway, I'll just give you a quick rundown of the cyclic molecules that are out there. So let's start with this one. There's 3 sides. It's got 3 carbons. It's a propane. You call it cyclopropane, although it doesn't look like a cycle very much now, does it? Moving on, you've got the 4. Square. It's a butane, so you call it cyclobutane. This is 5, it's a pentagon, cyclopentane, and down here, 6 sides, cyclohexane. Now you could go on and on and on, so you go cycloheptane, cyclooctane, cyclononane, but for the sake of not hurting myself over the inability to draw these shapes, I'm just going to leave it at these 4 so we get the general idea. Now let's take a look at the application of these to say substituent groups and other things like that, because you'll see it's very much similar to what we've been talking about for the last 20 minutes or so. So this has 6 sides. It's a hexane, cyclohexane actually. You start counting from over here because this one has 2 substituent molecules coming out of it. If you had one over here, you start counting here and work your way this way. These are both methanes, and this is an ethane, but it's actually an ethyl, obviously, so methyl ethyl. You start counting at 1. So you have 1,1 dimethyl, 1, 2, 3, 4, 4-ethyl cyclohexane. But you actually put ethyl before methyl if you remember. So it's 4-ethyl, 1,1 dimethyl cyclohexane. And if you had, say, a double bond there, it would be a cyclohexene, because that applies to cyclic molecules as much as it does to normal lines. Now there's another thing that I haven't talked about, but that I won't talk about, and that's the cycloalkyl groups. It's basically where each of those cyclic molecules comes off of, say, instead of a methyl group on a normal line, you have one of those. So it basically looks like a line with a line in like a square or a triangle or something like that coming out of it. And for the purposes of the AP exam, that's not necessary to know, so I'm not going to go over it right now. So that's it for the naming of compounds. Some people think it's hard. Once I got it, I thought it was relatively simple and straightforward. But again, it's necessary to really understand it. All you need is common sense. There's no math, equations, memorization, except for a little bit here and there, but nothing too bad. But it's all stuff you should be able to get relatively easy. And it also helps you because you have a base now in organic chemistry. And more importantly, you can brag to your friends and tell them, yeah, I'm doing organic chem. What kind of chem are you doing? Oh yeah, wait. Doing inorganic chem. You're an inorganic boy. You're not. Because in the end, that's all that really matters. Bragging, right? So, thank you. Bye-bye.